Welcome back to Maths in an Empty Classroom with me, Mr. Southern. This is part 2 of the lesson on using identities to solve reciprocal trig equations, and in this video I'm going to take you through an example using the Pythagorean identities, which I call squaredy swappies. Okay. So first of all, you'll notice that at the top of my board I've written an identity that you should already be familiar with from your studies of trig, which is sine squared plus cos squared equals 1, sine squared theta plus cos squared theta equals 1. And I've written it twice. And the reason I've written it twice is there are two further identities that look similar to these that involve reciprocal trig functions. The first one is obtained by dividing this whole equation through by cos squared theta. So if I do that to each term, I divide each one by cos squared theta, and I just have to think about what I get by doing that. Well, sine theta over cos theta would be tan theta, that's the identity we used in the previous video, which means that sine squared theta over cos squared theta is tan squared theta. Cos squared theta over cos squared theta, well, if you divide something by itself, it's 1, so plus 1. And then 1 over cos squared theta, well, 1 over cos theta is sec theta, so therefore 1 over cos squared theta is sec squared theta. So there's the first of my two identities that I call squaredy swappies. Tan squared theta plus 1 equals sec squared theta. So I put that in a red box because that's very important. And to derive the other one, rather than dividing the equation through by cos squared theta, we divide through by sine squared theta and think about what we'd get there. So again, divide all three terms, this time by sine squared theta, and consider what we end up with. Well, sine squared theta over sine squared theta, anything divided by itself is 1, plus, now, cos over sine, cos theta over sine theta, it's the identity we used previously, it's cot theta. So by that same logic, cos squared theta over sine squared theta is cot squared theta. And then finally 1 over sine theta, well, 1 over sine theta is cosec theta, so 1 over sine squared theta is cosec squared theta. And that is the other Pythagorean identity using reciprocal trig functions, two identities worth learning and being fluent with. So tan squared theta plus 1 equals sec squared theta, and 1 plus cot squared theta equals cosec squared theta. The way that I've just demonstrated to you to derive those identities, if you were asked as part of a question to show that these identities are true or to prove them, then that is an acceptable way of doing it. Start with sine squared theta plus cos squared theta equals 1, divide it all through by cos squared theta to get this one, divide it all through by sine squared theta to get this one. That's absolutely fine. Okay, so what we're going to move on to look at now is solving an equation involving one of these identities. And the equation that I have is 5 sec squared theta equals 2, and then in a bracket 7 tan theta plus 4. And I'm solving that between 0 and 360. So straight away I need to make sure that my calculator is in degrees mode, because that's the angle unit that I'm using here. Now, at the moment I have an equation that's difficult to solve because it's in terms of two different trig functions. It's got sec theta and tan theta in it. So what I need to be looking to do is to swap one of them using an identity so that I have everything in terms of one trig function. And what I'm going to do is I'm going to replace that sec squared theta with the identity that we've just derived, tan squared theta plus 1. So I've got my 5, and then in a bracket I'm replacing sec squared theta with tan squared theta plus 1, and that still equals to lots of 7 tan theta plus 4. That bit I haven't changed. So I'm now going to expand out the brackets on each side of the equation, which gives me 5 tan squared theta plus 5 is equal to 14 tan theta plus 8. What type of equation is that? It's a quadratic. What do quadratics have to equal before we can solve them? 0. So 5 tan squared theta, I'm going to subtract the 14 tan theta from both sides of the equation and subtract the 8 from both sides of the equation, giving me my quadratic 5 tan squared theta minus 14 tan theta minus 3. Now it's your choice how to proceed here. Some people are comfortable factorising it in this form. Other people like to use a substitution to get rid of the tan theta temporarily so that it looks a bit more normal, a bit more like what we're used to. So if we let y equal tan theta, what that changes the equation into is 5y squared minus 14y minus 3 equals 0. And some students are more comfortable with that, they find that more familiar, it looks more like a quadratic to them, and that's absolutely fine. Right, factorising that then, we would have 5y and y, negative 3 and positive 1 equaling 0, leading us to two solutions for y, which is that y is negative 1/5 and y is positive 3. But we just need to pause for a moment now and think, hang on a minute though, but I'm not interested in y, I'm interested in tan theta. So I now need to say, okay, if y is negative 1/5, it means that tan theta is negative 1/5, and if y is 3, that means that tan theta is 3. And what I'm going to do now is to solve each of these two equations separately to give me all the solutions for theta. So starting off with tan theta equals negative 1/5. I'm going to do tan inverse of negative 1/5, which comes out as negative 11.3, I believe. Negative 11.3, yeah, absolutely right. So negative 11.3. Now because of the negative, I am just going to draw this one out onto a quick cast diagram. So we have 0, 90, 180, 270, around to 360, A, S, T, C. And now because it's negative 11.3, rather than going anti-clockwise around the cast diagram, we go clockwise, and it's this angle in here, which is 11.3. Should make sense because that's in the cos quadrant where tan is negative and tan theta has a negative value here. So I need the other quadrant where tan is negative, which is sine, not the all and not the tan. So I draw in another line here with an angle of 11.3 in there. Now, starting on 0 and measuring anti-clockwise round, my first solution there is going to be 180 minus that 11.3, which is 168.7, that's to one decimal place. And the other one, starting at 0, and going all the way around, is going to be 360 minus 11.3. So just work out what that is here. That is 348.7 to one decimal place. And what you'll notice here is there's a difference of 180. That's because tan repeats every 180. So for my next set of solutions, when tan theta equals 3, I'm not going to draw a cast diagram on this one, I'm going to do this a bit more quickly. I'm going to do tan inverse of 3, which is 71.56. And then because I know it repeats every 180 degrees, I'm just going to add on 180 to 71.56. Which is going to give me 251.56. Okay. So I've got 4 solutions in total. Let's just take the time to tidy that up and present that nicely then. So 4 solutions for theta. Theta equals 71.6, that's to one decimal place, 168.7, 251.6, and 348.7. And those are my 4 solutions for theta, 2 of which came from tan theta equals -1/5, and 2 of which came from tan theta equals 3. But the key point was going back to the very original question. Eliminate sec squared theta by substituting tan squared theta plus 1. We did that so that everything was in terms of tan theta. We obtained a quadratic, which we solved, and then we made sure that we got all our answers for theta, and there were 4 of them in total. I'll see you in the next video.